today I'll be talking to you all about a few things related to pipelining. So you're going to learn about a pipelining language today. Maybe some of you are already familiar. The engine on which we run this pipelining language and sort of the infrastructure around it in terms of distributing this pipeline, sharing it amongst others, collaborating, editing it together as a group. So let's jump in. Okay. So how many of you have heard of WDL, Whittle, before, the workflow description language? Okay, great. So helps me understand how detailed I should go into this. But a lot of the GATK pipelines that Megan referenced earlier in the GitHub repo are all written in Whittle. It's essentially sort of a DSL to write scientific workflows. It can be agnostically written as well. It doesn't just have to be scientific workflows, but it's a way to sort of run an automated pipeline of analyses. And how it's actually executed is on an engine called Cromwell, and we'll go into details on Cromwell and how it works soon. And then Terra is sort of how we recommend people to write and run Whittle workflows, essentially. And so Terra is a portal that sort of supports editing of these workflows, building of these workflows, and then the execution of them using cloud resources. Okay, so here's sort of the high-level version of the GATK best practices workflow, right? And so when there are cases where it makes sense to use Whittle, and then there are cases where it doesn't make sense to use Whittle. So I think it's so important to ask yourself the question of the analysis you're about to write, and does pipelining make sense for you to do that in that case, right? So I think in a case where you have a lot of repetitive tasks and the structure of those tasks and the ordering of those tasks is about the same, then yeah, you probably are looking to build a pipeline for your needs. In the case where you want exact reproducibility over and over again between different samples and exact auditability, that's also a case where it makes sense to use a pipelining solution, right? Because a lot of pipelining solutions will keep track of exact events that went through, when they happened, and who did what, essentially. So that can be a useful thing. Definitely reducing human error is probably the biggest thing here, right? If something is just a well-established analysis, then it just doesn't need to be reinvented over and over again. And a good pipelining language and a good pipelining solution can kind of take care of most nuances needed for it to be flexible and repeatable at the same time. So I think that's probably the biggest reason people use pipelining solutions. And then I guess it's the same point as if something is consistent and validated and a good way to do things, then you probably want to build a pipeline. And I think sort of what's not here, but sort of the obvious is when you're sort of developing a task or you're developing an analysis, maybe that's not the right time to use a pipelining solution. So if something is sort of more established, you probably want to pipeline it. If something is less established, you probably want to do something a little more dynamic in that sense. Okay, so I think we're talking about a pipelining language, and how many of you have heard of other pipelining languages before, even other than Whittle? Okay, yeah, so maybe not too many of you, but if you just go and look for pipelining solutions out there, there are so many that are available. That ecosystem is very rich of options, right? So in the case of Whittle, is it truly the only pipelining solution out there? Not at all, not by any stretch of the imagination, but it's the one that we developed here, and it's the one we support heavily, right? So that's the choice of putting it on Terra because it's the one we can sort of have some control over and fix bugs and things like that, right? Systematically, just makes sense to focus here. And I think and I'll sort of walk through what are the other advantages of using Whittle, but I love this cartoon because I think it just shows that there are truly so many competing standards for pipelining solutions, and Whittle sort of adds to the ecosystem. So that can be a little bit confusing if you come from a very data science computational background, because you've probably seen other solutions already. So it does mean relearning things a little bit if you've used other pipelining solutions, but today I'm going to walk through how Whittle works, what are the core concepts for you to consider if you want to build a pipeline of your choice. So in Whittle, I think I want to use, okay, great. So the core concept in Whittle is essentially your workflow, and that's sort of the right-hand side here. And your workflow is sort of the end-to-end execution of all the tasks that are going to take place. And so sort of one level deeper, one level more atomic than a workflow is a task. So on the left-hand side here is a task. I think a perfect way to think about a task is sort of like a function. A task is a definition of a function, and it has something called inputs, like a function would. It has a command section, which is the actual executable that gets run somewhere. This is sort of a new concept of, you can define runtime parameters in a task. So let's say you're about to write a task that goes and aligns a piece of DNA. It's possible that you know that you need this many CPUs or this much disk space given the size of that sample and such. So you might want to fine-tune those parameters. So if you don't want to use built-in defaults and you really want to optimize for some kind of cost, or you really want to optimize for runtime, then you have the flexibility to go in there and switch things up. The other really important runtime parameter to consider is Docker. I'm going to dig into Docker a little bit, but essentially when you're running pipelines on the cloud or using the cloud to do any kind of analysis, in order for it to be sort of shareable and reproducible, Docker is probably the best practice in terms of building a sort of a boundary of software packages that you can use for your development and also share with your collaborators for the same development elsewhere. And of course, just like on any normal function, you have outputs in a task defined as well. So the important thing here, I think, to notice is that one has to be explicit when using Whittle, right? So only the inputs you define are the ones that the pipeline knows about, and only the outputs you also explicitly define are the ones that sort of get retained and saved. And if this command created a bunch of stuff, the only thing that's coming out of here is this one file called out. And all the extra stuff just gets thrown away, right? So one has to be really explicit when using sort of this language and thinking through what are the true inputs and outputs you want to preserve. Great. And then once you've built a task and the function you want to call, what happens is in the workflow definition, the workflow also has sort of inputs. These are more global inputs, so you can imagine some kind of reference file that you'd want to wire through multiple tasks in a workflow, right? That's sort of more of a global input. And so in this case, what's happening is, in this workflow, the user is calling some task called task A. So the call is sort of, you're turning on the function. You're about to go run the function. And then as a part of that call block, the inputs for that task that are required need to be wired in. So you can either like type out the actual inputs, you can use these global input variables, and then the task gets run. And then in this case, another sort of random task you can call task B is also here in the workflow definition, and it relies on the output from task A as input to task B, right? So given the fact that task B has a dependency on task A, the way this workflow is actually executed is that task A runs first, task B waits until the outputs of task A become available, and then task B executes. That's essentially what's happening here, and so Whittle kind of builds the graph of execution, and then sort of downstream of that, Cromwell is the thing that runs it. So go ahead.
Ask if they can be in a separate file or have to be in the same file.
Totally, that's a great question. So you just asked, can the tasks be in a separate file? Do they have to be in the same file? They can be in separate files. What's important is that when tasks are defined in a separate file, they have to be imported as a part of the workflow definition. So in the workflow file where the workflow is defined, there's a line you can add at the top that sort of does an import statement on that task. Any other questions here? Yeah, go ahead.
How would you, so in here it's pretty clear that task B is dependent on task A, but successful completion of a task is two different things. What is the success of a command or success of the process? How do you control that?
That's a great question, right? You're basically asking how is success defined here, right? So there's two aspects of it. So when using Whittle, if the output file doesn't exist, then that's not success. That's one aspect of it. The other thing is that if your process here, this command, exited with a non-zero return code, then that's also not success. So if your file exists, but you exited with a non-zero return code, that's failure. Right? So there's an implicit nuance here of it's not just the files, the process also has to complete successfully. There are sort of certain cases where maybe you don't mind that it didn't exit with a zero return code. There are sort of extra configurations you can put into your task to override and sort of ignore the return code entirely, because maybe that's not interesting to you. And you can sort of redefine success based on your exact function. There was a question here.
Say I don't want B to be dependent on A, and I want them to be parallelized. Can I do this?
You totally can, as long as task B doesn't have inputs coming from another task. If this dependency didn't exist and the input for task B was just some random input that you pass in, then they would run exactly in parallel. Yes?
Just to add about the success part, so can I define my own parameters saying that, imagine I'm running a tool star aligner, and after star finishes, I'm calling SAM tools to do sorting.
Yep.
So I can check my own parameter that if the file is produced and there is a sorted file from SAM tools, then it's a success. Otherwise, it passed star, but it failed SAM tools.
If you could find a way to, so in the case you're saying with the second task, you also want to validate that the file produced is sorted. If you can build in logic in your command to cancel out that zero return code, that would sort of synonymously also show the same thing, that the BAM's not sorted, then that would be one way to do it. I can think of a lot of different ways you can sort of tweak and build that logic in, but the general answer is yes, because the task is built to be super flexible, so you can have it fail in creative ways if you wanted to, essentially.
It's easier to implement in Whittle.
Yes, exactly. And a lot of people who, and yeah, we can definitely talk nuances. I'll be around, so if you're interested in, if you're trying to think about how to fit the kind of tools you use into a task and how you'd want to capture those failure modes, I'll be around to talk. Okay, great. I think these are sort of running things linearly is a common way to do things. Running things in parallel is another way to do things. And you can also do things like scatter jobs. So if you want to run the same function across a large set of inputs, right? That's a very common way to run a pipeline. Then there's all kinds of semantics built into the language, so you can do that with a few lines of code, essentially. Okay. How many of you have heard of Docker before? Okay, great. Okay. I feel like, I don't know if this was a shared experience. I think learning Docker for the first time can feel like an uphill battle because it's a new concept and it's a containerization technology. It means having to learn a little bit more about programming than I think maybe people would want to. So I think the activation energy can be high for Docker, but I always encourage people to learn it because once you know Docker, it really becomes a really powerful technology that you can leverage as a part of pipelining, but even outside of pipelining in terms of reproducibility. I think it's one of the strongest options out there. And so I think, and the other thing is the way we've implemented support for Whittle, for running processes on the cloud, we've enforced a Docker dependency. Because the point is we want the task to produce the exact same results no matter what cloud platform it's run on, as a way to just really enforce reproducibility when using this language, because that's one of the core principles of the language. So if you've already used Docker before, you kind of have an idea is that you've packaged all your software dependencies into a bundle, essentially. Even beyond your software dependencies, you can put pretty much anything in Docker. I don't recommend that. I think the smaller your Docker image, the better it is. But you can essentially, the world is your oyster on this. You can just fit your Docker with whatever you want. And then you can, the way we advise people when using Docker in Whittle is that you can sort of test locally that Docker. Because the most important thing here in terms of testing is that the command you're about to execute needs to be functional on the Docker image that you're using. And it's possible that when you change a Docker image or you use someone else's Docker image, things are installed slightly differently. So it's always a good thing to sort of, when developing this pipeline in Whittle, to sort of check the Docker and command functionalities locally. Okay. So we've talked about pipeline. Oh, go ahead.
Question about, so did you say that only Docker is supported for Whittle, or did you just any other container technology like similarity?
Ooh, good question. I think, at least running on the cloud. Oh, yes. The question here was, is Docker the only containerization technology supported by Whittle? So if you're running on the cloud, I feel Docker is the only technology available. I think if you're using Cromwell locally, so if you're using it with an HPC cluster, you should be able to use Singularity. Is that right, Khalid?
There are people experimenting with it. We We have not tried it ourselves, but
Yeah, and specifically for the community here, BITS and the research computing group are working on solutions for that to get, and there's a beautiful plan to make it easy to use Whittles and Cromwell through Singularity on Uyghur. Uyghur? How do you pronounce it? I don't
Both.
know.
I've heard
Uyghur?
both.
Uyghur. Okay. I mean, I made a big deal of pronunciation this morning, so I feel bad. Anyway, so there's a plan, at least for BroadE and BroadE affiliates, that is, there, I'm sure there'll be some communication soon, and you will be well served. To the rest of you at home, we'll figure something out in terms of documenting and spreading the word. And the solutions, once we have a good solution, we'll communicate it.
Thanks, Geraldine. There was a question.
Job. I'm here if anyone wants to talk. Yeah. I'm from BITS. If anyone wants to talk about that kind of stuff.
Great.
Yes. Yes. So Jared Bancroft, he's the expert. Talk to him.
Awesome. Anything else about Docker? All right. Okay, let's jump into Cromwell. So Cromwell is the engine we use to execute Whittle. So far, I've talked a lot about Whittle. Beyond Whittle, there's another pipelining language called the Common Workflow Language, CWL, that Cromwell supports running. How many of you have heard of CWL before or used it before? Okay, cool, yeah. So I think it's been out there even longer than Whittle, so likely you've run into it before. And I think the most important part of this visualization is the bottom half, is that one can sort of use Cromwell to execute on all kinds of different infrastructures, right? So if we start right to left, then Google Cloud is the one I've probably talked about the most, or maybe you've tried it yourself and used Google. We've recently added support for AWS. It is, because AWS is much more recent, it's a lot less mature as a result of time spent sort of refining that integration. So if you tried using Cromwell on AWS, you realized it's not nearly as smooth as Google, and we're sort of working to fix that support and kind of even that out. Additionally, if you're involved with GA4GA standards making and such, TESS is sort of a GA4GH API for task execution, so Cromwell supports that. Cromwell can also run on Alibaba Cloud, and that was actually an external contribution into our code base because there were a few people trying to use Cromwell using Alibaba. This is probably the most interesting to you, is that Cromwell can run locally, so you can run and execute jobs on your laptop. But on top of that, you can run Cromwell against any HPC. Well, maybe not any HPC, but a lot of like the commonly available HPC infrastructures. So if you're using SGE or LSF, things like that, then you can configure your Cromwell to talk to that cluster. Additionally, if you happen to have an LSF cluster, say on AWS or Google Cloud, I think that's a very recent thing that they've added, you can even use Cromwell to run on that infrastructure as well. That's also a little more beta, but I've talked to a few users who are experimenting running Cromwell against a cloud-based LSF cluster. Questions here? Okay, so with Cromwell and Terra in general, what we're trying to do is sort of shift the approach in terms of how analysis happens in the research environment. So I think the key differences, I think, are listed here. So the traditional way of accessing and using data is every institute, or even within labs, there's redundant copies of data that people have. And so that's essentially everyone has their own store of data that they use when doing analyses. With the Terra approach and the cloud approach, the point is to put data in some kind of centralized location, put the right access boundaries around it and the right solutions in terms of granting access to new users, and then using that as a source of truth and like a common well for sharing data. The other sort of important thing here is that every institute and every sort of group has their own approach to similar concepts. So if you talk to 5 different institutions, I'm sure they all do pipelining completely differently. So, and the goal here is to sort of create a centralized approach, and Cromwell is a piece of that, but I would say Terra is sort of the larger story around how to reduce that very similar but slightly different infrastructure everywhere. Of course, I think the biggest thing here is that when you have a local cluster, you have fixed compute. So you're often depending on the busyness of essentially the use of that cluster that day. You may or may not be queued. And that's often the problem that people run into when using local resources. And if you care about security implications and the type of data you're using and the way it flows through different services, it really matters that you have auditability and secureness in how that data flows. Then it's also really important to have sort of a centralized and monitored secure implementation of this framework to run pipelines. Question?
On Firecloud, we have issues with sharing data because we were big when people wanted to download data. Is there a way in Terra to ask people to pay when they want to download data?
Oh, are you saying that in Firecloud there was no support for something like requester pays data, right? That's a great point. And right now, that's still a restriction in Terra, but this is something we're adding support for very, very, very soon. So you should see like some kind of announcement, I want to say in the next month, just discussing what it means to have requester pays support in Terra and how to enable it. So.
Because yeah, we are going to either implement something to manage this
or you'd rather use a pre-implemented solution. Yes, no, that makes sense. But it's coming very, very soon. It's under testing and stuff right now. Other questions? Cool. Okay. I think this graph sort of just hammers like what it means to, or what are sort of the analysis patterns for a lot of people doing research, right? That it's not often like a steady flow of work that's going on, that a lot of research that happens at the BroadE, even if you look at sort of the BroadE graphs of the local compute cluster and how it's used in that, is that things are very spiky in terms of usage. So you do a bunch of analyses and then you walk away. Then you come back and do a bunch more and then you walk away, right? So having sort of a fixed model of this compute is always available isn't the best use of those resources. And one of the key reasons we sort of encourage the usage of cloud resources is that you can use them elastically. So you basically pay for them when you're using them. I think it's really important to kind of point out here that there are sort of different nuances in terms of how cloud billing works and how provisioning of resources in the cloud works. That's not exactly the same as on-prem resources. So there's definitely a learning curve here on moving to the cloud. But the reason we encourage it is that we feel once you're used to the cloud model, at the end of the day, there is going to be more efficient use of resources. And over time, you should see sort of like your bill come down once you become used to how to use the cloud, right? But at the start of it, it's going to feel a little bit uphill for sure. Okay, so this is sort of a high-level model of how Cromwell operates. I think it can be helpful to know, although you don't have to remember these details in order to use Cromwell, but it's good to know in the back of your mind how things work and how information flows, because that could be useful for you when you're debugging. So here's us. And then you have your command line tools, something like GATK, and then you can wrap them up into some kind of pipelining solution like Whittle, and then you throw them at Cromwell to go and execute. And so here we see sort of two approaches to those two biggest ways Cromwell is used today is that you can use it to run locally, so you could connect to your SGE cluster. And the way this works is that Cromwell knows how to access files on the NFS system and kind of moves things around as it needs to, because it has a very specific directory structure on how inputs and outputs are managed, so there is sort of a lot of file copying that kind of happens. And it doesn't have to be copies, but it can link the files to sort of reduce your footprint of copying and such, but you can optimize Cromwell to run locally. The other way to run Cromwell, which is really popular today, is using Google Cloud. And the way this happens is that Cromwell uses Google has a genomics API, and that's what Cromwell uses to hook into the Google Cloud platform. And what this API does essentially is that depending on how you specified your runtime parameter for CPU, memory, and maybe you haven't, and there are defaults behind the scenes that it's using, the first thing it does is that it provisions out of your quota of machines that you have, it provisions a machine where it's going to run your task. And then the way data is stored in the cloud is on these like buckets using object store. So then it localizes and delocalizes, which are just words for copies data in and out of that machine. So the first step is literally making copies of your data from that bucket onto that local machine, running the task as defined in your command block against the Docker as defined in your runtime parameters, and then sort of gathering the outputs as explicitly defined, and then copying them back out to a bucket. And then everything else on that machine gets thrown away and deleted. Question?
So the cloud is not a great environment for developing a pipeline because it costs money as you're debugging.
Totally.
So it looks like, so we would hope to be able to sort of develop either on our laptops or on like on Azure or something like that. Use and then be able to easily like test it there and then easily move to the cloud. Are people doing this?
I feel like my recommendation is always test locally. And if you're testing locally, you just want to, which can be intensive on your laptop, the more you can downsample your data, the easier it'll be to test locally, right? That is the key to testing locally. So finding a downsampled data set, building a pipeline, using Docker to iterate through it, and once it looks good, you'll put it on the cloud. Will it run the first time through and through? Probably not. Because the thing about moving from downsampled data to larger data is that the resource requirements now change, right? The memory you need per task for the exact same job changes. The disk space you need changes. So there's that curve of like now when you're using real-size data on the cloud, you'll have to make adjustments. But once those adjustments are done right, then everything should be a lot more smooth.
I just wanted to add really quick. This is the method by which we develop our pipelines. We develop them locally on an SGE cluster, and then we take them the same script to the cloud and run it there at scale. So definitely possible. The transition is fairly easy, but there's always more testing. But yeah.
Absolutely. And there are certain functionalities in the pipelining language that makes it easier to do things like you have a bunch of inputs. So and when you're running in the cloud, you have to specify exactly how much disk space you want, right? That's common operation. So there's a function called size in Whittle where you can say, yeah, these are my inputs. Can you just get the size of my inputs? And whatever that is, double it and give me that much disk, right? So you can sort of think about how you'd want to solve the problem if you just knew all the information. So that way there's ways to kind of tweak the expressions you need in the language to do some of the resource requirements. Things like CPU and memory can be harder depending on the tool you use because it can vary on the efficiency of the tool you use, which are things that I feel like you hadn't had to think about when running things locally, but things you're forced to consider when running on the cloud. Question?
So as of today, to do local development, you can develop your code locally on your laptop or Azure, but you cannot really debug your Dockers on Azure because you can't run Dockers on Azure, right? You have to do it on your laptop.
Yeah, so that is the true limitation, that if you really want to run, if you want to test locally and use Docker, then you can't use SGE. And that's where I feel like my recommendation is always downsample your data, so that's a good way to sort of test the combination. Take data out of the equation and test your command and your Docker together, and then take it the next step of like use real-size data, keep the same Docker, and fiddle with your requirements.
So when Singularity is compatible with this system, you will be able to run send engine with Singularity.
I'm sorry, say that again?
So with Singularity instead of Docker, you can run Singularity as a job in your local cluster and do it.
Exactly. You just made a good point that if you had Singularity, then you can basically have the same sort of Docker testing on SGE, and that would be ideal. So yeah, I think if we can get Singularity support, then testing locally before moving to the cloud gets a lot easier. Totally agreed. Question? I saw another hand. Okay. Great. I feel like we actually talked about this deeply just now. So you can sort of, there's multiple ways to use, never mind, this is different. So there's one way to use Cromwell, which is that you can deploy to the cloud if you wanted to, but you could always do it from your command line. So you can always run Cromwell from your terminal and send jobs to the cloud. That's one way to do it. That means you manage that server, you manage whatever database Cromwell is using, and sort of keep track of things a little bit. Another way to use Cromwell is use a portal that also deploys its own Cromwell, manages its own Cromwell as a way to reduce that overhead on you in terms of managing the engine and throw it onto the portal that's running the server. So there's a lot of other benefits to using portals like Terra and Firecloud, even just beyond running Cromwell, right? Because there are sort of all these auxiliary pieces to this journey, even before running workflows and even after running workflows, right? So upstream of being able to run pipelines, you need access to data. Maybe before you run your own pipeline, you want to look at sample pipelines. So where do you go to look at example public Whittle pipelines that you can use to get started? So those are functionalities built into Firecloud and Terra. Where do you go? Once you've written your pipeline and you want to share it with the people in your lab, how do you do it easily? You can share that file and like make copies of it all around, or you can share it as a method in one of these portals and distribute it more easily and kind of keep version history there as well. So there's sort of all these things upstream and downstream of pipelining, which is where I think the portals come in. So if you want to share the results of that data, it all kind of gets encapsulated in a workspace. So all the pipelining you do in Terra, the outputs of that get stored in a data boundary called a workspace. And so that if your lab has access to that workspace, by nature they have access to like all the experiments you're running. So it's very easy to share like, this is what I found and this is the data I have, instead of you having to do the work of distributing it and such. And this is sort of a secure data boundary. So we take on the burden of like making sure that only the right people who have read access to it do have read access to it and things like that. Kind of the security work around that. Okay. This is sort of the end-to-end flow of how one would run pipelines in Terra. I feel like it can feel busy at first, and this will probably make more sense once you've gone through the hands-on portion of how to run a pipeline in Terra. But this is essentially the full flow of the information as things happen. So you start off as the researcher, you've built a pipeline, that's great. You've maybe tested it out and run workflows, and you've run them on the cloud. Okay, so that's good. So you've developed locally, and even when you develop locally, you can submit to your laptop, and even when you develop locally, you can still submit to the cloud, so maybe you've gone all the way. And then when you step into Terra, it's more of, usually when you step into Terra, the first thing you'll do is build a workspace for yourself. Your workspace is your sandbox. There's really no other complexity there. It's just your own private space. And that's where you go in and you store your method somewhere and you import it into your workspace. You store some data into the bucket linked to your workspace. And depending on how you store your data, you might want to structure your data into a data model view, which I think of as sort of a tabular view of your data. So you can either think of your data as just files in a bucket, or maybe you think of them as samples with attributes. Like this is the BAM file for it, this is the FASTQ for it. These are the outputs for that sample, the history of that sample. So that's where the data model can be useful. And then you combine your method and your data to go and execute the pipeline. And in this case, the execution happens via Cromwell, which now you know everything about. And Cromwell is relying on Google's genomics API to hook into the cloud. And then at the end of the day, at the end of the stack, we're really just using Google Compute Engine to run the stuff. So like if you played around with GCE before and grabbed an instance and tried running things on it, that's essentially what Cromwell is orchestrating for you. And then additionally, Terra can hook into different data libraries. And your data doesn't have to just live in the workspace where you're working. The data can live outside, and you can still sort of refer to it and still access it, as long as you put access in the right places. Cool. So I think a really useful functionality of Terra is that it provides showcase workflows and tutorials to kind of kickstart on this journey, right? I think it can be kind of hard to start from scratch when writing any pipeline. So the most useful thing is you can kind of come in and check to see maybe the pipeline you already want is already there. Maybe it's mostly there and not all there. You go to look at one of these and it gets you 50% of the way through and not all the way, but at least you'll be able to use something to model off of. And I think another great part about these showcase tutorials is that they're well benchmarked. So you can see, like, okay, on input data of this size, I expect it to run for this long, and I expect it to cost this much money, which can be sort of a new thing if you're stepping into the cloud for the first time, is like that cost, and the way that cost is handled is a little bit different. So it gives you a chance to sort of look and see, okay, yeah, this is what I should expect in terms of cost. And the other way to run pipelines as well is in a more interactive manner, is using something like Jupyter Notebooks. How many of you have used Jupyter Notebooks? Okay, cool. So Jupyter is just a great way to run and execute Python and R and just like a more interactive session for sort of development of code. You can actually run pipelines through that as well. In this case, you'll lose some of the auditability and reproducibility because maybe you're changing your versions of your software and things like that. In this case, this environment is a little more interactive, but one could still pipeline on it. But I think the true value of this environment is to do development. So we were talking about before you pipeline something, maybe you're iterating through the stages of the exact tasks you want to run, the order you want to run them in, things like that. That's where I feel the notebook environment is more useful, is sort of upstream of pipelining. You'd want to go in, figure out exactly the tasks you want to run, and then this is also a great place to come in and do some visualizations on the outputs you've generated. Let's say you run a pipeline that you like on some sample set that was meaningful to you, and then you'd want to come in here and you can swoop in the data from your bucket and run some kind of visualization and to kind of validate the outputs you've generated. And you kind of have free form to do that. Okay, great, that's it. Any questions? Yeah.
I don't know, you mentioned about cost. For example, for situation where people are affiliated to BroadE but they are paid from another institution. Does the BroadE provide any support to use Terra? I mean, cost-wise or not? If you're aware.
That's a good question. I'm not sure if there are discounts for BroadE affiliates using the cloud. Was that your question? That for people who are collaborators with the BroadE, but not necessarily at the BroadE, affiliated with the BroadE, but not at the BroadE, are there any sort of like cloud discounts?
No, there's not any like discounts on the cost of using Google. One really important advantage of being, if you're an affiliate, if you can, I think if you do your work through a BroadE billing project, then you get coverage on our on the enterprise support plan. So you get better support from Google Cloud. Yeah, so that's kind of a priority thing if you're with the BroadE.
Yeah. Great. Thanks, everybody. Oh, yeah.
Just a quick question. The Google Genomics API, you're saying that you're starting to support AWS as well. So what changes there?
So we're using something called the AWS Batch API, which is it's fairly synonymous to the Genomics API. So we're keeping that same interface, but talking to an AWS-specific API that does the same things, essentially. Great.
So one final question.
Yes.
This question has been bugging me for a long time, and I've never gotten a proper answer. What's with the pig?
Oh, what's with the pig? I'm going to let Geraldine answer. That's all her.
Oh man, the pig. That was a 3 a.m. conversation on Slack. Yeah, there were attenuating circumstances. Man, on the record, the story of the pig really is of why it looks like that is Cromwell, as the name Cromwell for the engine, as an homage to James Cromwell, the American actor who played famously in Babe, the movie with the little pig, and also was Zephram Cochrane, the inventor of warp drive in Star Trek First Contact, Star Trek 8. And so it's a pig with warp nacelles as an homage to James Cromwell. That's the story we're going with. There you go.